Hey guys, this is Professor Janacek. I want to go over some integration by substitution. In these examples, we're going to have some definite intervals, meaning we'll have some limits of integration. The thing to remember about those limits of integration, they begin as x values, but then they change to u values because remember, for substitution, u is equal to g of x, so we end up having to change those limits of integration values. So let's take a look at example 5 here. We're integrating from 0 to 2 of dx over x plus 3 raised to the third power there in the denominator. Now, I think it's convenient to go ahead and move that dx to the back so we can kind of keep that off to the side. Okay, so now I need to figure out what am I going to let u equal. Well, remember u is g of x, and that's kind of the inside of composition. And so if you look here at our integrand, I have inside the cubed, which is inside the denominator, we have x plus 3. So I think that's a good place to start. We'll let u equal x plus 3, which tells us then that du is simply dx. Oh, well, that's nice and simple. So we've got the integral. I'll get to the limits of integration here in a bit, but this is 1 over, remember, x plus 3 is u, so this is just 1 over u cubed, and du is dx, so I can just replace that with du. So now notice all of my variables are u's. Notice you'll never see me go from having some u's and some x's. It's either all x's, either all x's or all u's, but never a combination of the two. We need to keep our variables separate. Now, the one thing I do need to worry about here is my limits of integration. Notice I'm going, I've got x values of 0 and 2, and I need to change those to u values. So for x equal to 0, what is u? Well, u is x plus 3, so that's 0 plus 3, which gives us just 3. So instead of 0 as my lower limit of integration, I have 3. For the other one, when x is equal to 2, so again I'm taking this upper limit of integration. For x equal to 2, u again is x plus 3, so that's 2 plus 3, which is simply 5. So my upper limit of integration is 5. So we changed our variables, and we change our limit of integration. Now I can simply stay in terms of u. I don't have to change back to x's. Integrating 1 over u cubed. By the way, if you would prefer to look at that as u to the negative third du, you can. And so when we integrate that, don't forget how to integrate this stuff. So if I integrate u to some power, remember the way we integrate, it's backwards from differentiation. I add 1 to the exponent and then divide by that value. So watch those positives and negatives. We end up with, let's see, that's going to be a negative 1/2 times u to the negative 2, and we're going to evaluate this from 3 to 5. Because I need to evaluate a negative exponent, let's go ahead and make that a positive. So I'm going to write this as negative 1 over 2 times 1 over u squared. And then we'll evaluate from 3 to 5. Of course, you could go ahead and simplify that a bit more if you wanted before evaluating this, but I'll leave it in this form. So we have this evaluated at 5 minus evaluating this at 3. All right, now I'll let you guys take a moment, pause this if you need, and simplify that. Watch those positives and negatives. Be careful with all those fractions. Some of those denominators get a little large. Let's see, you should end up with, when it's all said and done, 8 over 225. Again, watch those fractions and watch those positives and negatives. But, all right, there you go. Let's take a look at example number 6. We're going to integrate from 0 to 4 of x over x squared plus 1 dx. Again, I think it is sometimes nice to go ahead and kind of move things around a bit. Let me move that x over. Now it's a little easier to see what's going on. If I want to pick a u, remember it's that inside function, and I notice that x squared plus 1 is in the denominator, so that's going to be my inside function. So that's where I'll start with for u. And if u is x squared plus 1, then du would be 2x dx. So this is nice, that's good. This whole u I want to have here in the back. Now I'm missing a bit. I'm missing that 2. But remember, we can multiply by 2. I could put that 2 in there. Oops. I'll put that 2 in there, but I have to balance it by multiplying by 1/2 out in the front. So now what we've got is 1/2 integral. I am going to hold off on writing down those limits of integration because I'm going to change this to u's here. So we have, notice here I have u in the denominator. So that gives me 1 over u. And then here in the back is all just du. So we're just going to integrate 1 over u du. That's not bad. But before we can do this integration, we need to change those limits of integration. So we start with x being 0. When x is 0, remember u is x squared plus 1. So we get u is 1. So instead of 0 as my lower limit of integration, I've got 1. When x is 4, u is, again, x squared plus 1, gives us 17. So instead of 4 as the upper limit of integration, we've got 17. There it is, 17. And now we integrate. So we've got the 1/2, integrating 1 over u. Oh, don't forget, this one gives us the natural log of u. Of course, we're evaluating this from 1 to 17. So that's 1/2 times the natural log of 17 minus 1/2 times the natural log of 1. But hopefully we all know, remember, that the natural log of 1 is 0. Can you remember why the natural log of 1 is 0? So that gives us 1/2 natural log of 17, because that last term just goes away. And there you go. Okay, let's take a look at the next one. We're integrating from 0 to pi over 2 of, oh dear, we have trigonometric functions. Sine to the 4th x times cosine x dx. Oh, are we going to have to integrate these trig functions? Let's see. Well, one thing I notice, I often do this. I'm going to keep this in terms of x's for just a moment. Instead of saying this is sine to the 4th x, I can remember that this is really sine x raised to the 4th power. And when it comes to this u substitution, u has to be that inside function, and now it's very obvious that u is sine x, again, the inside function. And so what about du? U is sine of x, du is cosine x dx. Don't forget that dx has to be attached to that when you're taking the derivative. That's technically the chain rule. So what do we have here? We are integrating u, remember u is sine, so I'm just going to replace sine x with u to the 4th, and then there in the back, all of this in the back, that's du. Ooh, lovely. So all we're integrating is u to the 4th du. Oh, how simple is that? I don't have to integrate a trig function. I just have to integrate u to the 4th du. But before we do that, we need to change our limits of integration. Remember, we started with x values. X is 0 and x is pi over 2, but we need to figure out what that is in terms of u's. So for x equal to 0, then u would be the sine of that value. So sine of 0, oh, the sine of 0 is 0. So my lower limit of integration is still 0. What about when x is the upper limit of integration, pi over 2? Well, then u is sine of pi over 2. Sine of pi over 2 is 1, so our upper limit of integration is 1. So here we are. We're going to integrate from 0 to 1 of u to the 4th du. Oh, that's not so bad. Integrating u to the 4th du is 1/5 u to the 5th. Evaluate that from 0 to 1. And it looks like we end up with just a 1/5. How about that? Not too bad, I hope. Enjoy!